Welcome to this video again. We are talking about now today we're going to be entering into a different aspect of special relativity. You know, in the previous videos that we've been doing, we did time dilation. So special relativity is composed of two parts. We have time dilation, and then we have length contraction. So we have time dilation, we have length contraction. We also talked about what time dilation is. So time dilation in special relativity is a phenomenon that talks about two different people not agreeing on the same time duration, not agreeing on the time duration for an event. For example, and we say there's a condition under which time dilation is experienced, and that condition is if the two different observers are moving or are traveling at different speeds. When they are traveling at speeds relative to one another. For example, when someone is in a spaceship and flies up possibly close to the speed of light, time for him, he begins to experience it to move faster, to tick slower than the person probably on this earth. I mean, you've watched NASA launch satellites into space on space rockets several times. So let's say there's someone in a spaceship being launched from this world, and that spaceship travels at a speed close to the speed of light. He begins to experience time to tick slower for him if he had a clock with him on board. He begins to experience that time tick slower for him compared to the person who's still here at the space station, not moving at all. So this is what time dilation talks about, and it's a component, or it's a part of a broader phenomenon called special relativity. Now, today, we've finished with time dilation in our previous videos. If you want to know what it is, you can go back to those videos and watch them again. Today we're going to be talking about length contraction. And like time dilation, it simply means the phenomenon whereby two different people do not agree. Unlike time dilation, which talks about people not agreeing on the time duration for an event, in length contraction, people do not agree on the length of an object measured, or on the distance between 2 points. And like time dilation, this comes into it starts being experienced when you're traveling close to the speed of light too. Not just close to the speed of light, but at any speed. And I'm going to be explaining to you why that's at the end of the whole thing about special and general relativity, which I intend to talk about with you. I'm going to explain why in our everyday life we don't seem to notice this phenomenon even though they take place. You see, so today we are going to be talking about length contraction and how Einstein came about these ideas, how he got to know that length is not absolute, just as he told us that time is not absolute. So how exactly did he get to know a thing which in our everyday life, in our everyday observations, we don't see? So how exactly did he come about them? So that's what I'm going to be explaining to you today. And we're going to be using some mathematics as well. So how exactly did Einstein come about this idea, length contraction? And like time dilation, he did a thought experiment. He imagined scenarios and he arrived at certain conclusions. And those conclusions are not only mathematically correct, they're also physically correct. Now, The first thing he did is he imagined somebody sitting in a train. He imagined somebody sitting in a train. Let's say this is a train. The person is seated inside, and he wants to measure the length of, say, this biro. You know, there are ways we can measure the length of this biro. One is to use physical apparatuses like a ruler to measure it from end to end, and then see, you just read off the graduations on the ruler, and then find out how long it is. You see, but in this case, we are not going to be. He imagined the person in the train to try to measure the length of this. What do you call it? The length of this biro. So he's going to measure the length of the biro without the aid of a physical apparatus. And what it means is he's going to be using mathematical tools. So yes, as it turns out, mathematics, especially the formulas that we have, are actual tools, of course, abstract tools we can use to measure, to get the right measurement of physical quantities. You know, for example, this ruler, it has several graduations on it. Here is inches, here we have millimeters, and then centimeters. But if you look at the middle of it, there's still a difference which we cannot measure accurately with this mirror, with this ruler. But with mathematics, we can measure to the last decimal place. We can measure to the last decimal place the actual amount, the actual size of physical quantities. For example, if you want to measure length, okay, Einstein imagines someone in a train. Let's say this is a train. The train is moving to this direction at a speed u meters per second. Now in this train, this person is going to measure the length of this biro. Now remember, for the person moving in a train, everything is happening at the same spot. So for him to measure the length of this biro, he doesn't have a ruler. So he found out a clever way to do it. So he attached a light bulb to this place, to one end of the mirror, to one end of the biro, and then he attached a mirror to the other end of it. When he switched on this bulb, the bulb sent a photon of light traveling to this point. So the photon of light moves in this direction, strike the surface of the plane mirror, and so the mirror reflected backwards to it. So to try to get the length of this biro, which for him is L1, he said, okay, he knows the speed at which light travels. You know, as soon as he switched on his light bulb here, the bulb sent a photon of light to this mirror and back. So he knows the speed of the photon of light to be c. This is a standard representation of the speed of light in physics. Is equal to, then the distance it moved, that's the entire length of the biro. You know, the photon of light covered this whole length and then came back. So it is going to be not just L but 2L, because it's to and fro, divided by time. So the time taken for him to measure the entire event, that is the moving of the particle of light from this point to this point and back, he measured it to be T1. You see, so for him, he can measure his T1 to be, when you do a cross multiplication here, you find out that the T1 is equal to 2L all over C. So he called this equation 1. Now this is for the person in the train. For him in the train, even though the train is moving, unless it's just very much like you in your car. So when your car going somewhere, if you do not hear the sound of the engine, and you do not look out of the window to see houses or trees and people moving past you, you have no way to tell that your car is moving. Especially when you turn and look at the other person sitting by your side. You see, you just don't have this feeling. You don't have a way of telling that you both are in a moving vehicle. You see, so in that car, in that train, sitting down there, when you want to carry out this measurement, it looks like you're just sitting in a point, and so everything happens in the same place. But he then imagined if someone is outside looking at a train moving at U meters per second. This person is outside here. He's watching the whole thing taking place. He's watching the person in the, what do you call it? In the train performing this experiment, putting a mirror at one end of the biro and the light source at the other end of the biro, and doing switching it on. The photon of light goes here and there. He measures the time. So this person looking in, watching what is happening, what would he see, and what would be the quantities he measures? So before the train started to move, the light source was here. And then the, what do you call it? The mirror is at this point. But as soon as he, because the train is moving to this direction. So as soon as this light bulb is switched on, the photon of light begins to travel from this place. Oh, sorry. As soon as the light bulb is switched on, the photon of light begins to move from this place to this place. It begins to travel. But it won't hit this mirror at this point. It's going to hit the mirror at a point further down this line. Why? Because this train is also moving as he's seeing it. So instead of the photon of light hitting the mirror here, it won't hit it here, it will hit it somewhere at this point, which means it has had to travel more distance. Now, had it been the train is not moving, he's going to measure this length, which is L2. But the train is moving, which means the particle of light is not going to meet this mirror at this point, but somewhere at this point as the train moves. So the distance between here and here, let's call it D1. So the entire distance the photon of light moves to this place is not just L2 anymore, but L2 plus D1, because the car is moving. You see, so now we are trying to separate his experience, what he's seen, into two parts. Remember, in this place here, we didn't put it in two parts because for the person in this train, everything is happening at the same place. But for this one, everything is not happening at the same place. While the source of light, so the particle of light, was switched on at this point, it's not going to strike the mirror at this point. It will strike it further down the line. You see, so we are going to try to measure the time taken for it to travel to this point. And for this guy here, of course, C is equal to L2 plus D1 all over T2A. Now, I'm going to explain to you further down the line, why this whole thing is T2A. So to find the time taken for this particular light to cover this distance in the first part of the event, we have to do a cross multiplication. And when you do that, we're going to have T2A is equal to L2 plus D1 all over C. So this equation here gives the time taken for the particle of light to travel from this point to this point. You see. Now, but this D1, there is something we can still do here. This D1, remember, the whole train, according to this guy here, to this person here, the whole train is moving. He's sitting on the same place, on a bench at the train station, but the train is moving in this direction at a speed u meters per second. So from here we can deduce the value of D1 from this equation. So we can say we have u is equal to D1 all over T2A. Now first of all, this is equation 1. Let's call this one equation 2. So from here we can see that our D1, when you do a cross multiplication, this is going to become D is equal to U times the whole of this will give us UT2A. So let's call this equation 3. You see. Now, so we are going to put equation 3 in equation 2. And let's see what happens. So we have putting equation 3 in equation, putting equation 3 in equation 2, we are going to have T2A is equal to L2 plus, we remove this D here, and then we put the whole of equation 3. So it's going to become UT2A. See, so in this point, there's still something else we can do. We collect like terms. This has two T2A here, and this also has T2A. Sorry, all over C, because you know this equation has C here. So what we're going to do is we do a cross multiplication. So when you do that, we have T2A multiplied by C, it becomes CT2A is equal to L2 plus UT2A. So we have T2 here, we also have T2A. So we take this one to this side. So we have L2 is equal to CT2A plus, sorry, minus now, not plus, minus UT2A. Now, if you look here, we have a light, we can bring out a common factor from there. And what do we have? We have L2 is equal to T2A bracket C minus U. You see, so we can further break this one, to try to find the time taken for the whole of this to take place. So our T2A here is going to be, you divide both sides by C minus U. Divide here, so this one becomes bracket C minus U. And that implies that our T2A will be equal to L2 all over C minus U. So let's call this one equation 4. So equation 4 gives the time taken for the particle of light, in this case, to make the first round of trip. Now let's see the second round of trip. Sorry, the second round of the trip. So the second round of the trip, this is a train. We still have this guy looking at what this person in the train is doing. Now, the second part of the trip involves the particle of light making a return. You know, here It's moving this way, so the second part would have to be moving this way. So here is the mirror. Now, and here is the bulb, the light bulb. Now, at the time the photon of light started leaving here, the light bulb was at this point. But remember, as it is moving this way, this whole train is still moving in this direction, u meters per second. So, as it is, just when it started coming back here, this one was still here. But the whole train is moving, right? So as it is moving here, it is not going to move this entire distance anymore, because the whole train and everything is moving in this direction. So the light bulb, the photon of light, is not going to meet the light bulb at this length anymore. As this guy is looking in, he's going to see it at this point. Let's just see. Is going to meet it at this point, because this light bulb had traveled this distance. Now remember, this is still your L2, and now this one is not going to be D1 anymore, it's going to be D2. That's the distance that this bulb is going to cover, you see. So for the return trip, what is the time that is going to be measured there? We still bring out our equation again, that is C is equal to L2. Now it's not going to be plus like it was the case here anymore, but minus D2. Why? Because the what do you call it, the photon of light doesn't have to make all, it doesn't have to cover all this distance anymore. It doesn't have to cover this distance anymore. It had this, what do you call it, the bulb had already made the journey short for it by covering this distance, by coming to meet it. It is coming this way, and this bulb is coming this way, because the whole of the train is moving in this direction, you see. So it doesn't have to cover this entire distance anymore. It only has to cover this short distance now. So the entire distance it covers is not going to be L plus D2 anymore, like it was the case here, but minus D2 all over T2B. Now the reason we have B here is to differentiate the time measured by this person in the second phase of the journey. You know, in this case, this T2A indicates the time measured by this person in the first phase of the journey, which involves the photon of light traveling to the mirror. So from here, what are we going to do? We make T2B subject to the formula. So it goes here and this one comes down. So it becomes T2B is equal to L2 minus D2 all over C. We call this equation 5. But just like we did here, just as we did here, we are still going to do the same thing here too. Our D2, remember, the whole train is moving in this direction at this speed. So it is U is equal to D2 all over T2B, which is, when you do a cross multiplication, you're going to have your D2 as equal to U T2B. So this is equation 6. So we're going to put this equation 6 into this equation 5. So we have T2B is equal to L2 minus UT2B all over C. Now, when you do a cross multiplication, we're going to have, this is going to multiply this, while this one begins to stand alone. So what we're going to do is, we do a cross multiplication. This one is going to multiply this here, while this one begins to stand alone. So we have T2B, sorry, C T2B is equal to L2 minus UT2B. You see, it becomes this way. Now we're going to try to collect like terms. The whole of this will have to go here. So this becomes CT2B plus UT2B is equal to L2, because this minus will have to change to positive sign, and that's what we have here. So from here we can bring out a like terms, sorry, the common factor. So the common factor here will be T2B bracket C plus U is equal to L2. So this is what we have. So when you bring out the common factor from here, we have something like this. So to make sure our T2B stands alone as a subject to the formula, we divide both sides by C plus U, C plus U. So now this goes into this. Now this one can stand alone. It becomes T2B is equal to L2 over C plus U. So now we now have our T2B, which is the time taken for the return trip of the particle of light. But remember, this whole thing is not about time. We are talking about the length contraction. The idea that two different people may not measure the same length, or sorry, length for two different people may not always be the same. It depends on how fast they are moving, they are traveling relative to one another. You see, but if you look at what we've been doing here, you can see that we've been talking about time. The reason is we just don't have any other way to come about the relationship between the time this person, sorry, the length this person measures, the person in the train, and the length this person measures of the same object. We don't have that. So the only way we can do it is to first of all come from this direction. You see, so now we have T2B. We now have we have our T2A already, which is this, and now we have our T2B, which is equation 7. Sorry, this is equation 7, our T2B, equation 7. So this is the whole of this becomes equation 7. But you know, for this person here, the person sitting in the mirror in the train, we didn't differentiate the time for him. It was just T1. The reason for that is there was no need to break the person's experience into two parts. Why? Because everything happens at the same spot. But the reason why we had to break this one's experience into two parts, that is, as the photon of light travels from this place to this place and then back, is because two different things happened. The first one is the length of path this photon of light had to cover is longer in the first place, while in the second place it is shorter. Why? Because this whole train is moving, is traveling in this direction. You see, while for the person in the train, even though he's been traveling, he doesn't experience the same thing in the same way. You see, everything happens just at the same spot. So while the time taken for the whole thing to take place for this person is T1, the time taken for this person for both the to and the fro trip of the particle of light is going to be T2. And what is T2? T2 is going to be the time taken for the first trip to take place plus the time taken for the second trip to take place, which is T2A plus T2B. I hope something is clear to you now. You see? Okay, let me write this one here again. So the time taken for this person would be the time taken for the photon to make this first trip and then come back again, which is T2 is equal to T2A plus T2B. You see, and what is T2A? T2A is our equation 4 here, which is, L to all over C minus U plus, bring down this plus, T2B, which is equation 7, L to all over C plus U. So what do we do here now? We're going to try to collect, what is the LCM of this? It's going to be C minus U, C plus U. So this, the whole of this divided by this will be left with this one. So we have L2 multiplied by this. It will become L bracket C plus U plus this plus here, bring it down. Then the whole of this divided by this, you get this one remaining. So L2 multiplied by this will give us L2 bracket C minus U. So what are we going to do? Remember, the whole of this is equal to T2. So the next thing we're going to do here is to expand these brackets. So we have L times L2 times C will give us L2C plus L2 times U will give us L2U plus, you bring down this plus here. Now L2 times C will give us L2C, then L2 multiplied by minus U will give us minus L2U all over. You expand this bracket again, that is multiply the whole of this by the whole of this. So C multiplied by C will give us C squared. C multiplied by plus U will give us plus CU. Minus U multiplied by C will give us minus CU. Minus U multiplied by U will give us minus U squared. You see, now if you look here, we can properly arrange them. We bring together the L2Cs and bring together the L2Us. So the L2C, we have L2C plus L2C plus L2U minus L2U all over. Now first of all, L2U minus L2U, of course this is going to give us 0, which means the whole of this has been cancelled out of the equation. They're no longer there. In this case too, we have CU minus CU. Of course, anything minus itself gives us 0. So the whole of these two have eliminated themselves from the equation. So we have C squared minus U squared. You see. So now remember, there's something I want to explain here. We are talking about special relativity. Special relativity. And there are two components of it: time dilation and length contraction. We say as long as there is no net speed between two different people, then the time they measure for the time they measure when they observe the same event will be the same thing. There'll be no difference. But as soon as there is a difference in their speed, no matter how little it is, then time begins to dilate for the person moving faster. Now, it looks like magic, but it's not. It's actually real. By the end of the whole video on special and general relativity, which I intend to make, I'm going to explain why it doesn't look to us in our everyday life, even though it's still there. You see? So, now, and we also, the condition under which time dilates is the same condition under which length contracts. That is, if you have two people and there is no observable net difference, no difference in their speed, the relative speed between them, then if they want to measure the length of, say, this biro I'm carrying in my hand, they'll measure the same thing as long as there is no difference in their speed. But as soon as there's a difference in their speed, no matter how little the speed is, then the length of this biro the both of them want to measure won't be the same anymore. It is going to shrink for one of the observers, like you're going to see at the end of this video. You see, so the point that I want to make is this. While since the condition for time dilation to become a real experience, since the condition for it is the same condition for this, it means that as long as as long as there is a net speed between the two different observers. There's an observer in here. He's the one carrying out this experiment. There is another observer here looking at what this person is doing. This person is carrying out this whole experiment inside. For him, this is what he sees. But for this person, looking at what he is doing, he sees this. You see, which is also this one in the return trip. You see, so in special relativity, it's not just length that is contracting, but time is also dilating as well. Now, I want to find a way to resolve length contraction. I want to find a way, we have our L2 here, or to find a relationship between the length this person measures and the length this person measures. We have to find a way to equate L1 and L2. But if you look at this equation here, there is no L1. There is L2 here, but there's no L1. So we're going to try to look for a very smart way to bring in L1 into the whole equation so we can find their relationship. You see? But before we do that, let's still clean up certain things here. Let's tidy up certain things here. We have T2 is equal to L2C plus L2C will give us 2L2C all over. If you look here, okay, all over C squared minus U squared. Now, but if you look, we can still do more tidying up here. There's so many C's around. We have to try to remove them to the barest minimum. And how do we do that? We can do that by bringing out a common factor from here. Finding a very clever way to bring out C squared here, while the equation still remains the same, so that we can now eliminate this C and one of the C's here. And how do we do that? We can do that by We can do that by saying we have T2 here, which is equal to 2L2C all over. We can do that by dividing everything here by C squared. So when you divide here by C squared, what do you get? Okay, sorry, you bring out C, which is a common factor here. So here becomes C squared bracket. When you divide here by C squared here, you get 1 minus C squared, sorry, U squared divided by C squared will be the same thing. U squared all over C squared. So this is what we have. So that when you expand this bracket, you're still going to get C squared minus U squared. Because C squared times 1 is C squared. C squared times U squared divided by C squared will give us U squared. So the same thing is still there. So now we are going to cancel out this C. Take that one out, and then one of these ones too. So we have T2 is equal to 2L2 all over C bracket 1 minus U square over C square. You see, it's brilliant. But one more thing, what I was trying to explain to you here, we are going to, now this is what we are going to do it. What we are trying to look for is not time, because we've already done time dilation before. What we're trying to do, of course, part of general relativity, special relativity, is that it's not just that length contracts. Sorry, it's not just that time dilates, but length also contracts. And these two happen simultaneously. We've done a time dilation before. What we're interested in now is length contraction. So we are going to try to see if truly the length of the same object two different people measure are different. Now, through the mathematics, we can show it to those who are comfortable with mathematics. For those who are not comfortable with it, we'll try to find other ways to do it. Now, I cannot figure out how to verify this physically, but I encourage you to be patient with me. As soon as I find it, I'm going to bring it to those of you who are not very comfortable with mathematics. It is fine. So here we already have a L2 here. We're going to have to find a very clever way to bring in our L1 into this whole equation, and then find the relationship between the L2 and the L1 and see for ourselves if truly, at least mathematically, L2 will be different from L1, even though, L2 will be different from L1 as measured by the two different people, even though they are measuring the same thing. So here, so the clever way we are going to try to bring in our L1 here is to first of all realize that while length is contracting, time is also dilating. And we know from time dilation that T2 is equal to T1 all over the square root of 1 minus U square over C squared, right? You remember this equation. You can go back to the previous videos and see for yourself. So in place of T2, we're going to have to put the whole of this in there. So it becomes, so this equation here, equation 8, becomes T1 divided by the square root of 1 minus U squared over C squared is equal to 2L2 all over C multiplied by 1 minus U squared over C squared raised to the power of minus 1. Yes. So now, if you look here, we have t1 here now. So a very clever way we can still bring in a L, L1 is not here yet. But we know from our first equation that t1 is equal to the whole of this. That means we're going to put the whole of this first equation in place of t1 in this equation here. So now, this equation 9 becomes, you remove t1 and put 2L all over C. So we have 2L all over C multiplied by, bracket 1 minus u squared over c squared raised to the power of minus 1 over 2, which is equal to 2L2 all over C multiplied by, of course we wrote this one in index form, but we can still write it this way, it's fine, 1 minus u squared over c squared. You see? So now if you look here, we have c here, we have c here, so they can cancel each other out. We also have 2 here, we have 2 here, they can cancel each other out as well. So the equation is now reduced to L bracket 1 minus u squared over c squared raised to the power of 1 all over 2 is equal to L2 all over 1 minus u squared over c squared. Now I'm going to tell you why this one here became the whole of this raised to the power 1 minus 1 over 2. Now, anything in mathematics, if you have 1 over x, is the same thing as x raised to the power minus 1. If you have x, the square root of x, is the same thing as x raised to the power of 1 all over 2. And so when you have 1 all over the square root of x, what you're going to have is, you remember, 1 over anything is that thing raised to the power of minus 1, right? But then again, x raised to the power of the square root of x is the same thing as x raised to the power of 1 all over 2. And that's what we have here. So this is what the square root sign here can be transformed into an index form, which is multiplied by 1 all over 2, right? So the whole thing gives you, the whole of this becomes x raised to the power of minus 1 all over 2. You see, where this x stands for everything in this place. You see, so that's why the whole of this became this way, like you have here. If you have any question, you can ask in the comment section, and I'm going to try to answer it for you. Now, so we have this equation here, equation 10, the whole of this here. Now we're going to try to do a cross multiplication. Remember, the whole of this is all over 1. So this one multiplied by this will give us L bracket 1 minus u squared over c squared. Since this one is the same as this one is raised to the power of 1. Remember, so as it multiplies this, in indices, when we have, this whole thing is going to become multiplied by 1 minus 1 all over 2 is equal to L2. Now the reason why it is 1 minus 1 all over 2 is, if you have x raised to the power of a multiplied by x raised to the power of b, what you're going to do is to, as long as the bases are the same, we're going to bring one of them out and then add up the powers, which is a plus b, as long as it's a multiplication sign that is between them. If we had, let's say, a division sign, x raised to the power of b, this is going to be x raised to the power a minus b. These are the laws of indices. You see, so I'm trying to explain to you why we have 1 minus 1 over 2 here. You know, this one is 1. So if it multiplies this, remember, everything here is the same as everything inside here. So if you have the same thing with bases, with powers, multiplying one another, you bring out only one of them, which is what we have here. And then we add up their powers. So 1 plus bracket 1 minus 1 over 2 is the same thing as 1 minus 1 over 2. So 1 minus half will give us half, right? So this whole equation 11, this whole equation becomes this. So this whole equation 11, becomes 1 minus 1 over 2 is the same thing as 1 all over 2. So we have, so this becomes L bracket 1 minus U square over C square raised to the power of 1 all over 2 is equal to L2. Now remember what I told you here, that the square root of x is the same thing as x raised to the power minus 1 over 2. You see? So anything raised to the power of half, 1 over 2, is the same thing as the square root of that thing. You understand? So here we have L1. L1 multiplied by this bracket raised to the power of half. So the whole thing here still becomes L1, the square root of 1 minus U square over C square is equal to L2. You see? So this one is equation 12. So equation 12 here gives the relationship between the length the two different observers measure as they try to measure the length of the same object. You see? This equation here gives the relationship between the length this observer measures and the length this observer measures. This observer, the length he measures, which is L1, and the length this person measures, which is L2. So this is the relationship between them. So from here, if you have a L1 and the speed at which the train is moving, we can find that L2, and we'll find out, for those of you who understand a bit of mathematics, that this one here will always be shorter than this in the direction of motion. So that's it for this video for today. If you have any question, you can ask me in the comments, and if you can also rewind the video to listen to the parts which you're not very clear about. Thank you very much.